Hello, my name is Ron Frizard, and this is the first part of a 5-part series on how to pack a pump with mechanical packing. This series is going to cover all the facets of installation of pump packing. We're going to break them down into small, manageable steps. First one we're going to cover is common failure modes of pump packing. After that, we're going to talk about how to measure and inspect the stuffing box that we're actually going to put the packing into. Next, we're going to talk about lantern ring basics, how the lantern ring works, and issues like that. Next, we're going to talk about how to stick packing into the box and how to make sure it goes in correctly. Last, we're going to talk about starting up the pump. The best chance to understand how well the pump packing is working and diagnose a problem is to look at the rings as they come out of the stuffing box. So as you are removing the packing from the stuffing box using packing pullers and trying not to score or damage the shaft, keep them in a bag and label them, if possible, where they're located into the pump. If the rings are hard to get out, you could also use a degreasing solvent to help loosen the packing. Once you have the packing out of the box, you can now look for common packing failure modes. The number one issue that we see for premature packing failure is solid embedment into the ID of the packing ring. These solids stop the packing from forming a tight seal on the rotating shaft, creating uncontrollable leakage. Solid embedment is caused because of a poor flush system. Could be such things as poor flush pressure, poor flush quality, meaning solids trapped into the flush water, or lantern ring dislocation. We will discuss this in more detail in the third video of this series. The second issue to look for while reviewing the rings is glazing, which is really burning of the PTFE that's inside of packing rings. PTFE is a polymer that has a high thermal growth rate and a transition temperature at about 500 degrees F. That takes something from soft to very hard. This can be done very easily when you over-tighten PTFE, where the heat from the shaft can actually cause the packing to grow and create like a runaway train situation where we can get up to the 260 C or 500 degrees F temperature limit. Signs of glazing are rings that come out of the stuffing box hard and stiff. Also, there's a distinct smell of burnt plastic. Also, you might see shaft wear or actually shaft damage. The best remedy to solve this problem is to change the fiber to either a carbon graphite that can't glaze or a glaze resistant fiber like Nomex. The third most common failure mode is the wrong packing was selected for that application. This could be either the wrong size packing or one that can't handle the parameters of that equipment. For example, the temperature range, the pH range, or the speed range. We'll talk more about the sizing issue in the next video, but let's talk about if it was out of range by such things as chemical attack. If that's the case, it leaves the packing brittle and mushy. If it's over its temperature range and shaft speed, it will really show signs of fiber fracturing and burning. And if any of these are seen, you really should review the technical limits of the packing selected with all the chemicals and that the packing will come into contact with, including cleaning materials. Hey, the last issue to look for is related to the pump clearances. Packing is trying to create a tight seal in the stuffing box, and excessive clearances can lower the sealing load, resulting in leakage and constant adjustments. The telltale sign is extrusion of the packing rings. The remedy is to look at tightening up the clearances of the pump. This could include new bearings or a new gland if needed. Use an anti-extrusion ring at the bottom of the box or at the top of the box that has a stronger yarn could also help. In this video, we're going to look at what to measure to make sure we get the correct size packing installed into the pump. There are 4 critical dimensions that are needed to determine the right packing size and arrangement. They are the shaft size or sleeve if there's one over the shaft, the stuffing box ID, the stuffing box depth, and the lantern location inside the stuffing box. The shaft / sleeve size is one of the easiest to measure because it can be done quite accurately by using only a vernier. Some things to look for is making sure there is no step in the shaft or if there is any damage on the sleeve. The stuffing box ID is not so easy to measure since it is hard to get into the stuffing box and get a good measurement of the opening. Using tools like an inside-outside caliper can help. One trick is to machine down the ends so they can squeeze into the small opening. Another way to measure it is to measure the OD of the gland nose and use feeler gauges to get in between the gaps. This is not the best way, but for small openings, it is as accurate as it can get without totally dismantling the pump. To measure the depth, the best way is a simple 6-inch flexible scale that can be inserted into the stuffing box. It is always a good idea to get a few measurements. For example, taking multiple measurements of the stuffing box depth can make sure there is not something in the bottom of the box that could really affect the packing's effectiveness of sealing. One measurement that can often be overlooked is locating where the lantern ring comes into the stuffing box. A poor way to do this is just to measure the outside port and think that the lantern ring goes perpendicular to the stuffing box. This is not often the case. The best way to measure the distance is by taking a welding rod and inserting it into the lantern ring port on the pump. Sometimes the lantern ring is angled. This would mean you will need to find where it enters the stuffing box from the inside. The next step is to calculate the cross-section of the packing from the actual dimensions of the pump. The formula for this is simple. Just take the stuffing box ID and subtract the shaft/sleeve size and divide by 2. Now you should check to see if that cross-section fits a nominal size of packing. It could be either imperial or metric. This is very important since just guessing or using the cross-section of the ring before, you could have the wrong size selected, resulting in inaccurate sealing. The next important step is to inspect the gland and the bottom of the box and see what type of clearances the pump has. Wide gaps will make it hard for packing to create a seal over time since the packing will extrude into these gaps, losing critical gland forces and resulting in uncontrollable leakage. To find these gaps on the gland is relatively easy. Measure the OD of the gland and measure any gaps between it and the pump OD. Now on the ID of the gland, measure the gaps at 90-degree intervals, like 12, 3, 6, and 9, like on a clock face. From this, we can tell how centered the shaft is inside the stuffing box. The bottom clearances are harder to measure. A borescope will help show the bottom gap pretty well. The rings are still the best way to see if we have an extrusion issue at the bottom of the box, as we mentioned in the first video. It is just so hard to look and actually measure down there. This episode, we're going to cover the basics of the lantern ring. So let's get started. Lantern rings are one of the most confusing and misunderstood technologies in the pump industry today. The first thing to discuss is why one is needed in a pumping system. Today, with high-tech fibers and lubricants, there is no reason to use a flush for cooling or lubricating packing. The only reason to use a lantern ring with a flush is to keep solids out of the packing set. A clean flush without solids is used as a barrier fluid to keep solids from the pumping media embedding into the packing rings. Solid embedment into packing is one of the main failure modes of packing and can be stopped with a clean flush being used through a flush port. But also realize that if the pump's media is a clean fluid without any solids, no flush is needed. For a barrier fluid to work, it needs to always have higher pressure than the stuffing box. This is very important since sometimes the pressure of the flush is inconsistent, resulting in reversing the flow. Pressure of a flush should be set to 1 bar, about 14 psi, above the stuffing box pressure. The flush pressure becomes the new pressure in the packing, so if the flush pressure is considerably higher than 1 bar over stuffing box pressure, more force will be used to create a seal in the packing, resulting in shorter packing life. Flow into the stuffing box is important and is created by the differential pressures of the flush pressure and the stuffing box. Flow can be restricted by devices like an orifice type restriction, but remember, most flow meters are only restricting pressure, and you could get your flush pressure very close to stuffing box pressure, and that could result in no flow or a backflow situation. One issue that's still seen in the field has to do with misunderstanding lantern ring ports. Sometimes a pump will have 2 or more lantern ring ports. They were designed to get more flow to fill a larger cavity. Many times people are confused and assume this is a flow-in, flow-out pattern that's sometimes seen in a mechanical seal. Flush in a packed pump needs to be higher pressure on the lantern ring port in the stuffing box, and have a lower port open to atmosphere does not allow pressure to build up and results in mixing of fluids and solids building up in the packing, exactly what we're trying to stop. Clean flush is also a point to discuss. Many times a flush will not be totally clean. This can result in, again, what we are trying to stop, getting solids embedded into the packing. If a pump has no access to a clean flush, sometimes it is better to go without any flush than with a dirty one. Another major issue with lantern rings is the configuration inside the stuffing box. Many times there will be a set of packing below the lantern ring. These rings below are often forgotten about when repacking and can cause the lantern ring to slowly move into the stuffing box further past the lantern ring port. When this happens, flush water will spray out of the pump and at the same time is cut off, stopping solids embedment. Another major issue with these rings is that they do not provide any sealing but compress rapidly. That results in many adjustments and quicker time before the gland bottoms out, drastically lowering packing life. There are new technologies that actually replace the bottom rings and ensure perfect lantern ring alignment and save time of removal. A bushing can be used but can cause turbulent flow, resulting in mixing of fluids and migration of solids into the packing. EnviroSeal spiral track technology fills the area and also has a built-in lantern port that creates laminar flow in the direction of the shaft rotation. This plus its outer spiral makes for a drastic reduction in solid embedment and longer packing life. There are 2 types of spiral tracks for packed pumps. One is the type P that does not lower flush water unless a restriction device is installed on the flush, and the second is the first that has a built-in flush restriction. This episode we are going to cover cutting, inserting, and tightening pump packing. Sometimes bad habits that are developed when cutting packing rings can start at a plant and can severely limit packing performance. Training and education will help prevent bad maintenance practices and provide understanding of the importance of this task. Unacceptable practices for cutting packing rings can be handed down from technician to technician because it is hard to see the effect that it has on the sealing failure of the equipment. The most accurate way to cut packing rings is to use a mandrel that is the exact size of the shaft. By taking the mandrel and placing it in a vise and wrapping the packing around it, an accurate length can be determined for the packing ring. The ring shall either be cut on the mandrel at a 45-degree angle for a skive cut or a 5-degree angle, almost straight cut for a butt cut. Check the installation instructions of the packing manufacturer for the correct cutting type required by the application. Rings should be held tightly on the mandrel but not stretched. When cutting skive joints, a miter box should be used so that each successively ring can be cut at the same correct angle. After each ring is cut, it should be wrapped around the mandrel as a double check to ensure the ends adjoin with each other. This is similar to a go-no-go gauge. Skillfully cutting rings with a mandrel does take some practice. Focusing on the ends result where the rings fitting on the mandrel with no gap will quickly provide a feedback loop to perfect the practice. Each style of packing will pull around the mandrel slightly differently, so it's important to make sure each ring comes together perfectly. Cutting packing will always result in some waste. This could be rings that are too long or short, but also can be rings whose ends have unraveled or blossomed to the point at which they could result in a leak path. One of the easiest ways to sidestep errors in cutting is to order cut rings from the packing supplier. Besides no scrap, there is also a considerable time savings from not having to cut the rings. The drawbacks to using cut rings everywhere is having good documentation of the actual size of the packing beforehand to know what to order. Before installing the rings, it is a good idea to look at the bolts and make sure they are in good condition and do not have any corrosion or spots on the threads where the nut can't travel. Make sure a flat washer is used to make sure we are going to get a good smooth surface to tighten against with the bolt. Now we're going to install pump packing. One important point has to do with tamping the rings into the stuffing box. Packings need to be seated into its right location, and by just using the gland nose, you can't get the first couple of rings into the exact location in the stuffing box. This is where a tamping tool is used to make sure the packing is pushed into place. Without a tamping tool, rings will bunch up and cause serious performance issues before the packing will shift in the stuffing box. Some packings have a specific installation orientation. For example, dual pack technology has two types of fibers braided together. For extrusion-prone areas, the packing will be flipped 90 degrees to put the more durable fiber against the gaps. After installing each ring and tamping them into place, the gland should be pushed against the top ring and the bolt should be tightened finger tight. Now we are ready to start the pump. In this episode, we are going to cover starting the pump after installing the packing. One of the biggest issues with starting a packed pump has to do with understanding that the flush needs to be turned on before the pump is started. I've had many operators tell me that their training specifically told them to turn the pump on first before the flush. This is wrong. This floods the packing with solids and already starts embedment of the packing in the first couple of minutes of operation, reducing packing life and damaging shafts. Another critical issue that is often overlooked is breaking in packing right after installation. Tightening instructions from the manufacturer are important since fiber materials and lubricants react to heat differently. For example, a PTFE-based packing holds heat in and thermally expands drastically, resulting in excess heat to the point of glazing. Glazing of PTFE can cause harsh chemicals being released and hardening the packing that destroys shafts and does not seal. PTFE fibers or lubrication needs extra time to break in, making sure there is no heat wave being created that can cause glazing. Graphite and carbon fibers dissipate heat extremely well compared to PTFE and can be tightened at a faster rate. Continue tightening the pump packing until a controllable leakage is achieved. This term, controllable leakage, can mean different things to different people. It also has to do with many factors, including stuffing box dimensions compared to the packing size, the tolerance on the clearances in the box and the gland on the pump, the shaft centeredness in the box, and the quality of the pump packing being used. Regarding the quality of the packing, some issues to consider are the purity of the materials and the density and gaps in between the strands of the braid. This is based on the braiding machine's weights and tensions of the fiber during manufacture. Some packings can get to an extremely low leak rate, but with PTFE it is advised to keep some leakage since it is the only method to get frictional heat out of the stuffing box. Making adjustments on the packing is going to be based on a few factors. The biggest one is the number of rings in the box. 5 rings will have more consolidation than 3 and require more time and adjustments. Also, extrusion, as I mentioned earlier, will cause more adjustments. Another factor to consider is the larger the cross-section of packing, the larger the percent of compression, and the larger number of adjustments. One technology that can be used to lower the amount of times pump packing needs to be adjusted is rotary live loading. By using springs on the bolts of the pump, it gives more travel in the connection. When the packing consolidates, the springs move to cover the travel resulting in lower leakage during the consolidation period. This results in lowering the number of adjustments of the packing. Adjusting packing also should be part of any training program of operators. For example, many packing failures can occur when the packing is over-tightened during a retorque. Only short flats should be done, and if it is PTFE-based packing, there should be a time break between adjustments to allow for the packing to heat up and grow without glazing. Well, I hope you have enjoyed this 5-part series, and as I had stated before, if you have any further questions, feel free to contact our team. Thank you.